I think that we can now go straight to the next guest, who is Yaroslav Grosu from CIC Energy Gune, who will talk us about will deliver a talk about heat+work to electricity conversion via reversible water intrusion into hydrophobic nanopores. So let's leave the word to Yaroslav.
Thank you, Antonio, and thank you very much to organizers for giving me opportunity to talk during this nice workshop. So today I would like to share with you some of our results on how one can transform heat and work into useful electricity using intrusion-extrusion into nanopores. So I'll share my screen now, and please let me know if you can see my slides.
Yeah, we do. Thank you very much. Please
Great.
go.
So as I mentioned, this work is related with the phenomenon of intrusion-extrusion, and particularly intrusion-extrusion of water into hydrophobic nanopores for energy applications. It's a collaborative work, so I'll try to acknowledge as much as possible people involved in this work. So I'll start with sharing some background into intrusion-extrusion phenomena, so something which was already mentioned during this workshop by Carlo, Gaia, and Simone. But it will be more from experimental and more applied standpoint of view. Then I'll focus a bit on the nano-triboelectrification or contact electrification, which seems to take place during the intrusion-extrusion process, and how this can be used to convert simultaneously heat and work into electricity. And before concluding, I'll stop on the importance of intrusion-extrusion hysteresis. Okay, so to oversimplify the concept of intrusion-extrusion, you have to imagine any nanoporous material which is highly hydrophobic, meaning that the contact angle with water is at least 90 degrees or more. So those systems are interesting because due to high hydrophobicity of the porous material, the pores tend to be dry or empty under ambient conditions. However, one can force the water inside the pores by applying some pressure to the system. So particularly, for example, which is often the case, by putting the porous grains of porous material immersed in water and applying some pressure. So what's interesting about this system, that by reaching certain critical pressure, which we call intrusion pressure, the liquid can be forced, the water can be forced inside the pore. So on the pressure volume diagram, this is reflected in a plateau here, and this process is accompanied by accumulation of work of the system, which is intrusion pressure multiplied by delta V, which is the pore volume. But is also what is great about the system, that intrusion is typically, not always, but quite often, is endothermic process. So actually heat is also adsorbed to the system. Now, the process of intrusion-extrusion is typically hysteretic. So upon decompression, the extrusion pressure, so the pressure at which pores expulse the water and become dry, is much lower than the intrusion pressure. And during this extrusion process, system releases the mechanical work which was accumulated during intrusion, and also it releases heat during the exothermic extrusion. Now, this hysteresis can be very, very pronounced in terms of energy, which actually found its application in energy dissipation applications, particularly car shock absorbers, and this topic is not new. So it actually reached the application level where the car shock absorbers based on this phenomena were built and tested by several independent groups. And the fact that the work accumulated during the intrusion process is much larger than the work released during the extrusion process allows to dissipate mechanical energy, for example, energy of vibrations, like in this example, but also the heat which is absorbed by the system during the intrusion is typically much larger than the heat released during the extrusion, which helps to maintain those devices without overheating. So you may ask why I'm presenting, so why it is interesting to explore this topic if it's at such a high level application already. Well, this is quite fascinating, actually, a situation when the engineering community adopted this phenomena, even though there are a lot of things are not fully understood about this mechanism, because those systems, they work quite well. And one of the things which were puzzling for many years the scientific community actually is where the dissipated energy goes. So in simple words, if the work which is supplied to the system and the heat which is supplied to the system during intrusion are much larger than the released work and the released heat during the extrusion, where the energy goes actually. So the energy balance question arises here. So it was something we assumed that, well, if the work and heat does not provide the answer to the first law of thermodynamics, basically, perhaps there is electricity involved. And considering that we use nanoporous materials with quite pronounced surface area, the amount of solid-liquid interface, which is being mutually displaced during intrusion-extrusion is very large. So in fact, the effect of triboelectricity or contact electrification, which many of us know from the example of rubbing the balloon over the hair to get it charged. So this effect might be actually quite pronounced. So we decided to check experimentally whether that's the case. So this is the simplified setup we used for that. So basically we tried to measure work, heat, and electrical charge during the intrusion-extrusion process simultaneously. So that was a bit tricky to do, considering that we typically work at pressures up to 500 bars and sometimes more. This work was done in collaboration with Sebastian and Miroslav from University of Silesia. So we used several configurations to check the results by putting electrodes in different configurations. But independently on the configuration, what we actually observed, we were able to record a pronounced current exactly at the intrusion-extrusion pressures. So as you can see, these peaks of the generated current, they have the same sign during the intrusion-extrusion. The reason of that is because we are recording the current for the macroscopic system, so basically for the suspension of the particles in the liquid, and they seems to become equally charged both during intrusion-extrusion. So during the displacement of water inside the pores. Okay, so that was great. In fact, it helped to balance the energy equation in the cycle. And what is quite fascinating here, that the generated electrical energy is actually higher than the work supplied to the system. And the reason how one can obtain such values without violating the laws of thermodynamics is because the heat is involved in the process. So basically, why I'm providing only electrical to mechanical energies here, because typically in the applications of electric generators, the work is something which is counted as the input energy, while heat is something which basically can be absorbed from the environment, so essentially comes for free. So great numbers. Everybody likes efficiency more than 100%, basically. So this is to illustrate how it works. So basically, in the cycle during the compression and during the intrusion, the mechanical and thermal energy is being absorbed by the system while producing electrical energy. And during the extrusion, some of the mechanical and thermal energy is being released, and again by generating the electrical energy during the extrusion due to triboelectrification. So what is essential here is the heat in this process, because this is something which comes from the environment. So we are using here environmental heat, and so we would like to use as much as possible of it. And some of the systems actually demonstrate that this heat, the contribution of heat, can be much greater than the work in the system. So in this example, what we can see is for Z-fate metalorganic framework and water during the intrusion-extrusion, the heat which is generated, especially if we increase the temperature of the experiment a bit, the generated heat increases a lot with temperature, while the mechanical work not so much. So it stays more or less constant with the temperature, and this actually results in the fact that at a bit higher temperatures, the amount of heat absorbed in the system is around 3 times as compared to the work supplied to the system. Okay, so as you can see, basically the fact of so the amount of electrical energy which can be generated by the system comes from the hysteresis of mechanical and thermal energy during the intrusion-extrusion cycle. So it was actually very curious to see that once we apply this experiment on the electrification to the almost non-hysteretic system, which demonstrate nearly close to zero hysteresis in terms of mechanical work as well as heat, we actually saw no electrification effects within the precision of our equipment. So it's quite interesting to see that the underlying phenomena behind this behind this effect is at the nanoscale, but once we were working with macroscopic system, the energy balance sort of works pretty well here. So this material which we used here in non-hysteretic one is the metalorganic framework, which was developed by the team of Danli and Mianli. So hysteresis in the intrusion-extrusion process, as you can see, is very important because basically it defines the energy pool for the electrical energy to be generated. So therefore we put quite a lot of attention on investigating the intrusion-extrusion hysteresis. So for example, you may see you have already seen some of these results during this workshop presented by Simone. So here we looked into how the topology of mesoporous silica affects the intrusion-extrusion hysteresis. So it seems that both experiments and MD simulations suggest that providing conditions for the bubble nucleation during the extrusion is highly important to reduce the hysteresis in the cycle, and in fact in this case is to permit the reversibility of intrusion-extrusion process. And it seems that this statement is true not only for water. So here this is example of intrusion of mercury into mesoporous silica. Not that we are interested in using mercury for practical application, but just to generalize this observation, we explored the intrusion of mercury into highly ordered channels of MCM41 silica, and we saw the quite pronounced hysteresis of intrusion-extrusion. But once we use disordered pores, which provides a lot of small pores sites for the bubble nucleation, we actually saw almost no hysteresis in the intrusion-extrusion cycle. So this is quite promising in terms of generalizing this concept for liquids other than water. So as I mentioned before, some of the examples during this intrusion-extrusions involve metal-organic frameworks. Those are fascinating materials because they provide certain properties which are not available for rigid materials like silica or zeolites. But at the same time, they provide a lot of challenges actually in terms of the mechanism, how the intrusion-extrusion happens. So, for example, as you can see in these images, the intrusion-extrusion into Z-fate metal-organic framework qualitatively looks similar to the intrusion-extrusion into rigid materials like silica, for example. But looking into the structural behavior of the system during intrusion-extrusion cycle, which was obtained using in situ neutron scattering, one can see that the lattice parameter, or the unit cell in this case of the material, actually behaves very peculiar during the intrusion process, particularly during the intrusion of water. There is a very pronounced expansion of the unit cell. So this actually we can see this from the experiments, which was obtained with the collaboration of the authors. You can see on the bottom of the slide, and we can also see this from MD simulations obtained from the group you can see on the right. And this actually provides a lot of well, it's a lot of challenges in terms of how to see the process of intrusion-extrusion into MOFs, and whether the simple models can be used here to predict the electrification during the water displacement. So finally, about hysteresis, some notes on the dynamic hysteresis. So it's quite interesting that some materials they demonstrate this hysteresis of intrusion-extrusion to be quite independent on the compression rate. So you can see here on the left, for example, grafted silica, which is quite rigid material, and how its hysteresis is almost independent on the compression speed, even if we go to quite high rates of compression decompression. On the other hand, the more flexible materials like Z-fate metal-organic framework and this copper-based metal-organic framework, which I mentioned before, the hysteresis changes drastically as the flexibility increases for this material. So, for example, in this case, you can see that non-hysteretic material actually converted into something as which can be called as a shock absorber, because the hysteresis is very, very large here. So it's very curious for us to see how it affects the electrification during the intrusion-extrusion process. And in principle, from the previous statements from the energy balance, the expectation that that the rate of intrusion-extrusion should also affect the electrification, the amount of electrical energy generated during the intrusion-extrusion process. Okay, so to some extent, they conclude in a visual way the observed phenomena. It's quite interesting actually to compare these heterogeneous systems with typical working bodies which are used for energy applications. So most of the working bodies actually they produce some heat upon compression. So we transform some work into heat by compressing them. So this is quite typical for most of the materials we know. Now, for triboelectric generators, typically the energy balance looks something like this. So the work supplied to the system is transformed into electricity with some heat losses during the process. And what is fascinating about this intrusion-extrusion concept is that during the compression, the system absorbs environmental heat, and via triboelectrification can convert this work and heat into electricity. And with this regards the coefficient of performance, which for the applications is measured typically as the ratio between electrical output and work input, can be actually greater than 1. So something which which is quite fascinating to explore. So to conclude, the main points of this idea is that intrusion-extrusion of water into hydrophobic nanopores seems to be accompanied by the pronounced triboelectric effects, and those triboelectric effects can be used to transform simultaneously work and heat to electricity, for example, work of vibrations and environmental heat to some useful electricity. The fact that heat plays a considerable role in the energy balance of the system, the ratio between output electricity and input work can be greater than 100% in this case. And we hope to explore this phenomena for a wide range of applications like triboelectric generators and particularly regenerative car shock absorbers, which can generate electricity, which could be particularly useful for electric vehicles, for example, to extend the maximum range. So for more information, this is our recent papers on this work. We also started just this year the electro intrusion project, which is funded within FEAT proactive H2020 call. And yeah, and that's it. With that, I thank you for your attention. I hope the next time we will be able to meet in Rome for such a nice workshop, and next time the photo of my group would be without masks. So thank you very much for your attention, and if you have any questions, I'll be happy to answer them.
So let's thank Yaroslav for his very instructive talk, and let us also wait for a couple questions to pop up in chat, because I know there will be people typing right now. So let me first ask you a curiosity, Yaroslav. What do you think will be the next big thing in this topic? Or the main perspective that you foresee for the future? What you're really interested in? For these nanoporous materials and the energetic applications of nanoporous materials?
So we have several exciting challenges ahead of us in this sense. So one of the challenge seems to be how to maximize the charge transfer to be used. So at the moment, it seems that what we are doing, we are charging the particles during the intrusion-extrusion process, but considering that those particles are dielectric ones, it seems to be a bit difficult to fully collect the charge. The second quite challenging point here would be to maximize the heat of intrusion-extrusion, because this is the energy which we really want to use, because something which comes from the environment, and in most of the applications, something which is for free. So to go deeper into the mechanism of heat generation during intrusion-extrusion and to find a way to maximize it. Additional point which is extremely challenging is this topic is the stability of the porous materials. So a lot of those materials, they actually degrade during the intrusion-extrusion because we provide challenging conditions for those porous materials. So high pressure, high temperature sometimes, and gas penetration into the framework. So those are challenging things. And now we want to add actually electrification there. So I would say that that's the big thing also, so to develop the stable porous materials. If we are able to achieve all those things, the great exciting thing would be to build a prototype of regenerative shock absorber and to test it in the electrical vehicle. So the reason for this particular application is because the intrusion-extrusion itself for shock absorbing has been explored quite a lot. So in this sense, we're somehow introducing the new phenomena into technology, which is quite well developed. So I'm quite excited about this application. Perhaps this would be a next big step to achieve.
Thank you, Yaroslav. We have in chat, we have Armagan Kocher, who asks a very nice talk. Are we going to see this triboelectric phenomenon applied to electric cars? I guess you already commented a bit on this. And, If you have something more to add, otherwise I will just leave you to a short coffee break while we wait for our next great speaker.
So perhaps to add one thing in general in terms of applicability of this phenomena is that also there is a field of triboelectric generators which is known and actively being developed. So what I'm quite excited about this phenomena is that here we really can reach the ratio between output electrical energy and input mechanical energy higher than 100%, which is quite a disruptive thing in this field, because at the moment the best examples of triboelectric generators are something around 60, perhaps 70% of this ratio. So that's one of the things I'm quite excited about as well.
Thank you very much, Yaroslav.